Once again, good morning. This is AP Calculus AB. We're looking at the homework. 2.5 was due today. Now's your chance for any questions where you gave yourself an understanding rating of 0. What would you like to ask? Zoe, do you have a question? All right, so let's take a look at the last question. It's 3 pages of solutions, and the last question was number 75, tangent lines. To find the equations of both tangent lines to the ellipse, by the way, the radius in the x direction is 2, radius in the y direction is 3, passes through the point 4, 0. I've color-coded them. One of those tangent lines is orange, the other one is blue. So the first thing I did was come up with a formula for dy dx, the slope of the tangent line of all the tangent lines drawn to the ellipse using implicit differentiation. And that came out to dy dx is negative 9x over 4y. Are we okay with how we got to that point? Is there a specific question you'd like to ask about the solutions, or do you want me to just talk through it?
Like, I just don't understand after that how you work.
Okay, so after that, I explained my process. The equation of the orange tangent line using point slope form is based on the equation dy dx. So for m, I put in dy dx. Well, I'm just calling it m for now. M is the slope of the tangent line. And I did note that there's 3 unknowns here. M is unknown. I don't know the slope. I don't know x. I don't know y. Where x and y are variables. And so that motivated me to set up a system of 3 equations and 3 unknowns. So here's my 3 equations. One equation between x and y is the given equation. A second equation is that the slope is negative 9x over 4y. And a third equation is the equation of the tangent line. All 3 of those equations contain point A. The ellipse contains point A. The point A, you could think of point A as having coordinates x, y. So really what I'm trying to do here is I'm trying to find the coordinates of point A. And that resulted in, right here, I found out that x was equal to 1. When I was solving that system, I had to use substitution to do it. Once I found that x was equal to 1, I found the corresponding value of y. And if you think about it, what this means is that both point A and B have an x coordinate of 1. One has a positive y coordinate, the other has a negative y coordinate. And here's the positive y coordinate, positive 3 radical 3 over 2, negative radical 3 over 3 over 2. Now, friends, I think that one thing that might clarify any confusion you might be experiencing is that x and y represent the coordinates of point A. And I'm actually going to write this here. Point A will go dual user. Is located at x, y. And this is what it would be nice to know. It sure would be nice to know the coordinates of point A. Now, point A happens to be labeled in purple. So I'm going to change the color of this to purple to make that connection there. So now that you see what x and y represent, and therefore what my goal is, I would love to know the coordinates of point A. Because once you get the coordinates of point A, then we can use the coordinates of point A to find the slope of the tangent line. It's not so much that I need the coordinates of point A for point slope form, although I could have used those. I need the coordinates of point A in order to get the slope of the tangent line. Why can't I just use this point right here? Well, that's 4, 0. The y coordinate of 4, 0 is 0, and that would be division by 0. Besides, 4, 0 is not a point that's on the ellipse. I need a point that's on the ellipse. And so that's why I set up my system of 3 equations and 3 unknowns where point A has coordinates x comma y. Does that help clarify what's going on here? Okay, so I'm going to save this because that question that you asked prompts me to believe that at least putting this in here might help preempt that question for future years of calculus students, maybe even future generations. Further questions on the homework due today? Yes.
On that same
Lindsay.
one,
Yeah.
why couldn't you just use 1/4 and 1/9, like when you're finding the derivative, like the first part?
Yeah, so the question is, why can't I use 1/4 and 1/9? Help me understand where would I use 1/4 and 1/9? You mean x equals 1/4?
Yeah, like move like the 1/4 times x squared plus 1/9 y squared. Like why do you multiply it all by?
Why did I multiply by 36?
Yeah.
Because I don't like dealing with fractions.
Like could you just do 1/4?
Sure, I mean, there's other avenues, but you would get to the same answer. You'd get to the same answer for dy dx. Yeah. Yes,
So for
Marcus.
this question, you have to find the slope of this like original equation, and then you have to use that to find the slope of the tangent line.
Well, yeah, I mean, they're asking me to find the slope of the tangent line. So whatever the slope of the tangent line is, it's going to come from, I mean, it's got to be tangent to the ellipse. So that's what motivated me to find dy dx, which is the slopes of all the tangent lines.
So then why can't you just plug in like a point for like
Which point? Like this point, 4 comma 0?
Yeah.
Because that would give me division by 0. Anyway, dy dx represents the slopes of the tangent lines drawn to the graph of the ellipse, which means the x and y that I plug in has to be a point from the ellipse. The problem is I don't know which point to use from the ellipse. Which x comma y do we use? So I had to do some detective work. Say, well, it's got to be a point that's on the ellipse. It's also got to be a point that makes this equation true, and it's got to be a point on the orange tangent line. So those were the 3 things I knew to be true. Fortunately, that gave me 3 equations and 3 unknowns, and I could begin the process of solving by substitution. These were 3 things I knew that were true about the relationship between x and y for point A. All right, let's move on to today's lesson. I have asked you to do the review at the beginning here, and we have just quick review. Derivative of cx with respect to x is c. This is c times u prime. So watch out for the u primes here. And the derivative with respect to c, let's see, is u a function of t? U is a function of x, but it's not given that x is a function of t. And so that'd be 0. U and t are not related. U is a function of x, but it is not given that x is linked to t. So you got to watch out for this one. Might even call that a trick question. Here we got u prime plus or minus v prime. This is derivative of the first times the second plus first times the derivative of the second. No surprise there. Low d high minus high d low. Draw the line squared below. C times u of the n is going to be c times n times u of the n minus 1 times u prime. Because of TCR, the chain rule explains why that times u prime. A lot of people miss the times u prime. Did you miss the times u prime? Did you? Yeah. The chain rule is used every time you take the derivative. Here we go. And then down here, we're just taking the derivative with respect to x. So this is cosine x times dx dx, secant squared x times dx dx, which is 1. And secant x tangent x times dx dx, which is 1. So we got negative sine x, negative cosecant squared x, and negative cosecant x cotangent x times dx dx. By the way, just reviewing the chain rule, f prime times g of x times g prime of x times dx dx. And this one is f prime of g of u times g prime of u times u prime. So notice I didn't have to write dx here because it simplifies to 1, but I do have to write du dx, which is u prime over here. So that's the review. And I'm not going to take time to go over that a lot. That's just, it's a review of stuff you should know. And so you can use that to study. On this handout, implicit differentiation, we didn't finish all of this yesterday. I want to take a look at a couple of things that we did not look at yesterday on this. One is this page right here. It said find the point at which the graphs of the given equation has a vertical, horizontal, tangent line. So turn to the page in your handout that has this just for the sake of completeness on our notes. We're on Friday's schedule to go till 12:27. Okay, so I got to keep that in mind as we plan things out. There is a pre-calculus and a calculus approach to doing this problem. Let's look at the pre-calculus approach first. In pre-calculus, you're responsible for knowing how to complete the square. Let's collect all the terms that contain x together. We got 4x squared minus 8x. And then collect the terms that contain y, that's y squared plus 4y. And let's export the 4 to the other side, equals -4. Now, when you're completing the square in x, it's best to factor out this 4 first. I'm going to factor out a 4 to get x squared minus 2x plus blank, some number that I get by completing the square. Plus, and then in y, we have y squared plus 4y plus blank. We're going to complete the square in x. I'm going to put a double blank here with y equals -4 plus blank plus double blank. What number completes the square in x? X squared minus 2x plus what would be a perfect square trinomial, class? 1. So if I put a 1 here, what number do I have to put on the other side of the equation to counterbalance?
4.
A 4, because I really put a 1 times 4, which is 4, so I put a 4 over here. Likewise, what number completes the square over here, friends? 4, and since it's not being multiplied by anything other than 1, I just put a 4 here. So when I factor this, it's going to be x minus 1 quantity squared. I'm just factoring the trinomial. That was the whole point of completing the square, so I could factor it. So it's x minus 1 quantity squared plus y plus 2 quantity squared equals 4. And in order to see what's going on with this ellipse, I'm going to divide all 3 terms by 4 to get x minus 1 squared plus y plus 2 squared over 4, or I can think of that as 2 squared equals 1. Now we're in a standard form of an ellipse, so we can see where the horizontal and vertical tangent lines are by simply taking a non-calculus approach, just using our pre-calculus ellipse sketching skills. Hopefully, and if you didn't learn this in pre-calc, or if you forgot it, come and see me outside of class, but hopefully you're not too far away from remembering that this is an ellipse centered at 1, -2, with a radius in the x direction of 1 squared, which is, or of 1. So I'm going to go forwards and backwards 1 from 1 to get from 0 to 2. And the radius in the y direction is 2. So using pre-calculus sketching skills, I can now inspect this ellipse and determine that there are 2 points of vertical tangency, and in blue, 2 points of horizontal tangency and 2 points of vertical tangency. Horizontal tangents are in green, vertical tangents are in blue. Let's see, find points at which graphs, okay, so they're asking for points. So the answer using pre-calculus would be points at which there are horizontal tangents would be the points 1, 0 and 1, -4. What are the points, the ordered pairs at which we have vertical tangent lines? By inspecting the graph, it appears to be 0, -2 and 2, -2. Does anyone have any questions as to how I was able to obtain those 4 points using no calculus whatsoever? Okay, I don't see any hands up. Raise your hand if you understand that using a pre-calculus approach. Looks like there seems to be widespread indications of understanding. Now let's take a look at how we would start from scratch and do this problem using calculus instead. I'm going to, you know what? This is kind of a bold move, but I'm going to erase all the work I've done here so far. I mean, we have a video record of it, so you can go back and watch the video if you just, but I am gonna keep the answers here. Let's see how we could get these same 4 answers using calculus. As a warm-up, would you please use implicit differentiation to find dy dx? Go ahead and try it. Find dy dx using implicit differentiation.
Hi. How are you? Good. How's that music? What? How's that music?
Now, while you're working, I'm going to work up here to find dy dx using implicit differentiation. Okay. So it looks like the formula for the slopes of the tangent lines drawn to this ellipse, without even taking time to sketch the graph of the ellipse, just going through here and thinking that the 8 and the 8x will be exported to the other side. It'll be 8 minus 8x upstairs, and downstairs will be the binomial that remains once I factor the dy dx out of these 2 terms. Raise your hand if you're reasonably sure that you can correctly report to me the binomial that remains once you factor the dy dx out of these 2 terms. Looking for a volunteer. Yeah, Dana, go ahead. 2y plus 4 is correct. So we have 2y plus 4. This is the equation for the slopes of all the tangent lines drawn to that ellipse. So it's like, that would include the horizontal, vertical tangent lines. So using calculus, it's really not as much work. You don't have to complete the square. All you have to do is divide your work into 2 columns to find points of HT, horizontal tangency. That's 1 column. The other column will be where we find points of vertical tangency, VT. So here we go. Horizontal tangents occur when the slope of the tangent line is equal to what, class? Hello?
0.
0 is correct. So that's equal to 0. And if 8 minus 8x over 2y plus 4 is equal to 0, from that we can deduce that the numerator must be equal to 0. So 8 minus 8x must be equal to 0. So solve for x. Negative 8x equals negative 8, x equals 1. So the points of horizontal tangency occur when x is equal to 1. Look, that agrees with our pre-calculus approach. Both points of horizontal tangency had x equals 1. Can someone describe to me what would be the process to find the corresponding y values of 0 and negative 4? What would you end up doing? We found x equals 1. What would you do to find the corresponding values of y? Describe the process to me. I'm waiting for a volunteer to describe the process. What do you think, Peter?
Would you plug it back to the original equation?
Yeah, plug 1 in for x into the original equation. It'll be quadratic in y. And so you'll have to use the quadratic formula or factoring or something to find the corresponding values of y are 0 and negative 4. It's not that hard, but it is just algebra. There's no calculus there. Now, points of vertical tangency occur when, so dy dx is equal to 8 minus 8x over 2y plus 4. Points of vertical tangency occur when the slope is undefined. Slopes are undefined when the denominator is equal to 0. So you would set the denominator equal to 0 and conclude that those points of vertical tangency occur when y is negative 2. Notice again the harmony, the agreement with our pre-calculus approach. And just like Peter described moments ago, you would take this negative 2, plug, okay, let's plug. Not an official mathematical word. So we would substitute negative 2 in for y into the original equation, solve for x. It would be quadratic in x. So worst case scenarios, you'd have to use the quadratic formula. But you would discover when you solve for x that x equals 0 and x equals 2. But you would not be done until you paired up the x with the 2 y's, pair up the y with the 2 x's, you would have to then categorize your answer as 2 points of horizontal tangency and 2 points of vertical tangency. But as you can see, there's much less work to do when you are using calculus. The calculus approach is a shorter approach. Does anyone have any questions whatsoever on how to use calculus to get points, ordered pairs, of both horizontal tangency and points of vertical tangency? Zoe? Y equals -2? Up here? Y? Or-
Y equals 0 and y equals 4 for the horizontal.
Oh, yeah. Yeah. You would have to follow the process that Peter described. We didn't do it. We're skipping it. But what he said is go to the original equation, put a 1 in for x.
Oh, it goes,
To the original equation, put a 1 in for x, and solve for the corresponding values of y. Further questions? All right. Turn to the next page. And there's one thing I'd like to, instead of doing this problem, which would be fun to do, let's do something we've never done before, and that is find the derivative with respect to x of the natural log of x. By the way, does anyone think they know the answer, even though I haven't taught it to you? Does anyone think they know the derivative of natural log x? We've done the derivative of sine x, cosine x, e to the x, but we've never done this one. Who thinks they know what it is? Because I don't want to stand up here and teach you something that everyone already knows. Raise your hand if you're pretty sure you do not know what the derivative of natural log x is. Wow, everyone, Stephanie, do you know what it is? Everyone has indicated that they have no idea. Well, I'll tell you what, let's estimate it. Would all of you please sketch the graph before we actually use calculus? Would all of you please sketch the graph of the function y equals the natural log of the absolute value of x? It's a pre-calculus problem. Think of this as a little pre-calculus quiz. Sketch the graph of y equals the natural log of the absolute value of x. I'll give you 20 seconds to do that little review problem from pre-calc. My guess is that many of you have the right branch. Problem on, we have a test on this. Hopefully you have an intercept at 1, 0 and an increasing function. The rate at which it's increasing is decreasing. But because of the absolute value symbol, negative inputs are allowed. The domain is -infinity to infinity except for 0. So here's a graph of the natural log of the absolute value of x. Just pause here. Does anyone have any questions as to the reasonableness of this result? All right, now what I'd like you to do is use your get the graph of f prime based on the graph of f skills. Remember those skills? Gotta have skills. If there's anything Jack's taught us, it's gotta have skills. Use your skills of getting the graph of f prime from the graph of f. Try it. Just sketch it. Just sketch the graph of f prime given the graph of f. Sketch the graph. You'll need a pen or pencil for this. Take maybe 20 different points where you visualize the tangent line and then plot its slope as the y-coordinate on f prime. These slopes are negative, close to 0. Negative, maybe -1 right there. Approaching -infinity. I hope that your graph for f prime has 2 branches, 1 branch here, and then these are positive slopes close to infinity, positive slopes coming down, approaching 0. So if we were to say that the graph of f is green, and that other graph f prime is purple, then I could label this f prime. Raise your hand if you agree that this purple graph does appear to be f prime's graph. Thanks, you can put your hands on. Oh, by the way, which of the 50 parent graphs does this look like? It looks like 1 over x. I wonder if there's any way you and I could use calculus, more specifically implicit differentiation, to prove that the derivative of natural log x is 1 over x. Let's give it a go. Here we go. Calculus. Friends, would you please join me in writing down a starting point of y equals natural log of x. That's our starting point. Step one, y is the natural log of x. Now, to find the derivative of this, let's exponentiate. Because we don't know the derivative of natural log x, but if we exponentiate this, isn't it true that e to the y equals x, or in other words, that x equals e to the y? Does that look consistent with what you learned about logs back in Algebra 2? At this point, we can now use implicit differentiation to find y prime. Check this out. Let's differentiate both sides with respect to x implicitly. The derivative with respect to x of x is 1 dx dx. Would you please write down what is the derivative with respect to x of e to the blob, e to the y? Treat y as a blob. Try it. Write down what you think it is. What's the derivative with respect to x of e to the y? Raise your hand if you can tell me what to write down. It'd be kind of fun. You'll get to tell me what to do. You say stuff, I'll do it. As long as it's true. Dana?
E to the y dy dx.
E to the y, dy dx is correct. We're looking for dy dx, and dy dx has now come on stage. And so let's solve for dy dx. Dy dx equals 1 over e to the y. When you divide both sides by e to the y, you get 1 over e to the y. Wait a second, e to the y, that's x. We just did it. We proved that the derivative with respect to x of natural log x is 1 over x. This is a major result. Let's bring it to page 1. Let's record it. Top of page 1. We just found out once and for all. This is always going to be true. It's never going to be false. We just learned that the derivative with respect to x of natural log x is 1 over x. It looked like 1 over x when we did it graphically. We found out it really is 1 over x. That completes our lesson on implicit differentiation. Now to move on to the stuff that'll be on the homework for Monday. Related rates. This is the last section of new material for this unit. We're learning related rates today and Monday, quizzing it Tuesday, test on block day. And you know what else? I've decided to give you all the way until block day to finish the problem sets. So the problem set that you picked up yesterday, hopefully you have all the way until Thursday of next week to complete that. Let's look at our lesson on related rates. Now, when you take a look at your handout for related rates, you see that there's a little bit of review, and there's also a warm-up. Class, check this out. Reliving the Pelican situation. But this time, this oil spill, eyes up here. Some of you are not even looking. Look up here. Instead of dRdt being variable, this time, this oil spill is just expanding at a rate. The radius of the oil spill is expanding at 4 meters per second. So if this pelican can just fly at 4 meters per second, then he's in good shape. By the way, what is dAdt? What's the rate of change in the area of the oil spill with respect to time? Would you please take a moment to do this warm-up problem? What is dAdt when dRdt is 4? This is a warm-up problem. You may begin. I hope you came up with 8 pi r. I used implicit differentiation. I differentiated both sides with respect to t to get dA dt is 2 pi r dr dt. dr dt is given as 4. 2 times 4 is 8. So what that means is that, and just visualize this for a second, 8 pi r. If dA dt is 8 pi r, then that means, okay, so suppose this is at time 0, this is the radius. Suppose the radius, it's r. Then there's a change in r, delta r. After a change in r, then dA dt is 8 pi times change in r. So that means that delta A, which is a change in area, the area of this band, is 8 pi times the change in the, well, actually, it's just 8 pi times the current radius. So to say 8 pi dr is actually not correct. It's 8 pi r. 8 pi r. And then when there's another change in the radius, notice that the radius now, instead of being this big, is now that big. The change in the area is going to be 8 pi r. So what's happening here is that the rate at which the area is changing gets bigger and bigger as r increases. So, and I'm just going to make each one of these as dA dt. So dA dt, dA dt. I'm basically just copying this down. But the rate at which the area is growing, as you can see, it's not constant like it was before. We had dA dt equals 10. This time dA dt, it's growing faster and faster and faster. Well, that makes sense because each band has more and more area. Every time you add delta r, every time you add a little bit to the radius, I mean, it could be that you're adding 4 every second. dA dt is 4. You're adding 4 meters every second. So every second, the band has more and more area. So that's why dA dt has to be variable and not constant. Now, these are review problems. Let's get down to our first related rates problem, which is number 3. Very first problem in our last section. The radius of a sphere is increasing at a rate of 2 inches per minute. Find the rate of change of the volume of the sphere when r is 6 and when r is 24. Now, related rates problems can boggle the mind unless you humble yourself and use an organized approach. Sometimes students chafe against organization. But in journals I've seen in 18 years of teaching, 17 previous years of teaching AP Calculus, students every year, they thank me for this organization because otherwise, without it, they get MEGO. They're stricken with devastating cases of MEGO. MEGO, M-E-G-O. My eyes glaze over. These can be so mind-bogglingly challenging that students' eyes glaze over. It's like that stuff on the Krispy Kreme donuts. It's just really thick. Can't even see. Here's a structure that will help you cut through the confusion. It's a Roman numeral structure. Let's all do it together. In Roman numeral 1, you just draw a diagram of the situation. You draw it out. So in Roman numeral 1, draw a representation of a sphere with radius r. Also in Roman numeral 1, record the given derivative, which is dr dt, is 2 inches per minute. Everything has to have meaning. T is attached, meaning is attached to T using the word let T represent time. And they're asking us to find the rate of change in the volume. So we're going to let V represent volume of the sphere. And they're asking for dV dt. dV dt equals blank cubic inches per minute. Okay, that's Roman numeral 1. It's basically writing down the given information. Now, in Roman numeral 2, you write down what your goal is. We have to build an equation. What are the specifications? Well, it's always going to be these two letters. We want to find REL, a relationship between R and V. If you can find the relationship between the radius and the volume, then you'll have everything you need. That's Roman numeral 2. Roman numeral 3 is basically the main equation. And the main equation is always a mathematical relationship between the variables that are stated in 2. Again, it's my R and V look too similar. R and V. Now, maybe you forgot the formula for volume of a cube, but great change in volume. But if this were an AP problem, they would give it to you. Volume equals 4/3 pi r cubed is the formula for the volume of a cube. Now, this is just an introductory problem, so it doesn't have Roman numerals 4 and 5. So put this into the category of stuff for which you're going to have to trust that Mr. Royce knows what he's talking about. The next thing we could do is go to Roman numeral 6. We'll do problems that have Roman numerals 4 and 5 later. But Roman numeral 6 is where you differentiate with respect to time. Just like we did in the warm-up problem with the pelican, would you please differentiate both sides of this equation with respect to t? When you're done, look up here to see if you agree with mine. I came up with dv dt is 4 pi r squared times dr dt. That's the implicit differentiation. Remember, dr dt is 2. So they're asking us to find dv dt when r is equal, so dr dt is 2. So 2 times 4 is going to be 8 pi r squared. Here's the formula for finding it. So I have to find it when r is 6 inches. Are we all in inches here? Yeah, this is inches. So to answer this question, I have to evaluate dv dt when r equals 6 and also when r equals 24. I'm just going to do the first one. What's 36 times 8? 36 times 8, 6 times 8 is 48, 4, 24, 28. So it's 288 pi. So the answer to part A is 288 pi. Volume is inches cubed. Inches cubed per minute. Now that's a related rates problem. It's not too bad as long as you know implicit differentiation. Let's try another one. Try number 4. Number 4 says the side of a square x. So in Roman numeral 1, we're going to draw a square with side x. It's increasing. So dx dt is increasing at 3 centimeters per hour. Someone consider that slope. I'm going to call the area A. I'm going to let t equal time. It says find the rate of change in the area. So they're asking us to find dA dt when x equals 5 and when x equals 10. Would you please try to complete this problem on your own? Try to do Roman numerals 2, 3, and 6 on your own. You may begin. These don't take all that long. Hopefully you picked the letters A and X. It's always the upper right hand from the derivatives. You need a relationship between A and X. Class, what is the relationship between area of a square and X, the side? Call it out. That's right, it's A equals X squared. Once you have that, then you differentiate with respect to t. Go ahead and take the derivative with respect to t so we can answer the question. dx dt is given as 3. So the formula for finding dA dt is going to be 6x. So 6x evaluated when x equals 5 is going to be 30 centimeters squared per hour. Area is measured in centimeters squared. Now, those are our first two examples of doing related rates problems, and all of them have Roman numerals 1, 2, 3, and 6. I'd like you to attempt a few of those for homework. The homework is listed on the syllabus. Do that for Monday. We're gonna spend the whole day on Monday doing more related rates problems. Question, Jonathan?
For Roman numeral 2, does it matter? if it's made
Doesn't matter what
of
order,
x or
just need a mathematical relationship between the two. Because implicit differentiation, it doesn't matter whether it's solved for A or not. Okay, have a good weekend.